Cross-site scripting. What is it? How do we find it? And most importantly, how do we protect our websites against it? In this video, I'm going to answer all of these questions and walk you through exactly how XSS works with real hands-on examples you can try yourself. Whether you're just starting out or preparing for a security exam, stick around. This is gonna be practical and fun. Cross-site scripting, commonly known as XSS, is a type of injection attack where the attacker injects malicious scripts, usually JavaScript, into a vulnerable web application, which then executes the scripts in the victim's browser. Let me show you how this works with a very simple example attack scenario. So in this scenario, we have an attacker, we have our victim, and we have our vulnerable website. So the attacker first needs to find the target website that is vulnerable to XSS. We'll talk more about how that works later in this video. Then they deliver a malicious payload to a victim, which usually includes a JavaScript. Once the user visits the vulnerable application, the malicious payload is executed in their browser and the attacker receives the results. What kind of result do the attacker gets? The attacker is typically after something only the victim has access to, for example, cookies or session tokens, which can grant the attacker the same level of access as the user. So if the attacker obtains your session, they may be able to hijack your session, essentially log into the application as if they were you. In an XSS attack, the attacker may have different goals and try to achieve various objectives. However, they usually attempt to steal sensitive information from your browser, compromise user trust, or even bypass the same origin policy. But why is XSS so successful? From the browser's perspective, it trusts the script because it assumes it's coming from a legitimate user action, such as clicking a link or triggering a function. From the web application's perspective, it works because untrusted data, i.e. the user input, has not been properly validated or sanitized before being used. This data is then included in dynamic responses sent back to the user's browser without proper encoding, allowing malicious codes to execute. Before we jump into the details, let's see some real-world examples of how XSS has been used. A data breach impacted customer information from approximately 380,000 booking transactions. The company stated that names, addresses, email addresses, and sensitive payment card details were all compromised. What did the attacker do? They found a vulnerable web page and injected their own code, which altered the behavior of the websites for the users. The attacker did not necessarily need access to the backend server or database. Instead, they manipulated the front-end behavior. That's why the stolen data was limited to a specific time frame and included information that British Airways itself didn't even store. As another example, Checkpoint researchers discovered multiple security vulnerabilities in Fortnite, one of which could have allowed remote attackers to completely take over player accounts just by tricking users into clicking an unsuspecting link. By the way, Fortnite is an online gaming platform. The reported Fortnite flaw included SQL injection, cross-site scripting vulnerability, web application firewall bypass, and an OAuth account takeover issue. So as you can see, it wasn't just an XSS vulnerability, but XSS played a key role and the attackers chained multiple vulnerabilities to take control of the applications. So let's discuss different types of XSS. First, let's discuss reflected cross-site scripting. As the name suggests, a vulnerable application reflects user-controlled input without proper sanitization or encoding. For example, you enter your name, say Ali, and the application responds with "Welcome Ali." This is a simple case, but the concept is the same. In a reflected cross-site scripting, the attacker injects code via the URL or input field, and the server reflects that input back to the user's browser because the browser trusts the server. The malicious script gets executed. Here's a simple proof of concept code that you can see, and let's see how it behaves in the browser. Okay, so let's see a very simple example of reflected cross-site scripting. So this is the same code that we had and we showed in the slides. So if I open this with Firefox, as you recall, it would say welcome, and then it's waiting for a name suggestion. So I will add my name here, and it would say hello Ali, right? So what I can do to show it's vulnerable to cross-site scripting is to do a very simple proof of concept to pop up an alert and hit enter. So here we see that the browser is showing us an alert, and we just have to click on OK. So this is a very simple example of the existence of cross-site scripting, showing that we can create an alert message, and that's because the application receives the input, does not sanitize it, and then returns it back in the UI. The attack payload can be delivered to the victim in various ways, such as through email, SMS, social media platforms, or even by visiting a malicious website. Once the user clicks the link or submits a form, the browser sends the malicious payload to the vulnerable website, which then reflects it back and executes it in the victim's browser. The next type of XSS attacks is stored cross-site scripting. In the stored cross-site scripting, the vulnerable application receives untrusted input from the user and stores it, for example, in a database, in user logs, or other storage locations. The malicious payload is then served to any user who accesses or loads that data. For instance, imagine the attacker stores a script in the product comments section. Any customer who visits that page and loads the comments in their browser will be affected. This is what makes stored cross-site scripting more dangerous than reflected cross-site scripting, because multiple users can be impacted and not just simply one user. Stored XSS is also sometimes referred to as persistent XSS or type 2 cross-site scripting. Okay, moving up to the next type of cross-site scripting, DOM-based XSS. The document object model is a programming interface for web documents, including HTML and XML. In the DOM, the structure of a web page is represented as a tree, and each element on the page, such as paragraphs and buttons and links, is treated as an object. Developers can read and modify these objects using languages like JavaScript, which allows dynamic changes to the page. When it comes to DOM-based XSS, there are two important concepts to understand: source and sink. A source is where user input enters the application, for example, through the URL or a form field. A sink is where that data is used or rendered in the page, such as inserting text into the DOM or using inner HTML. Basically, the data flows from the source to the sink, and if it's not handled securely, it can lead to DOM-based cross-site scripting. Here are some examples of sources and sinks in DOM-based XSS. Let's look at some of the common sources. Document.url. So the document.url returns the full URL of the current page as a string. We also have location. Location, a property of the window object in JavaScript. It holds the current location and its components. Location.href, which is the full URL, location.search, which is the query string, location.hash, the fragment identifier, anything comes after the hash. Now let's look at some sinks. Document.write. Document.write writes content directly to the page. It interprets input as HTML, which means any untrusted data passed into it can execute JavaScript. This makes it a high-risk sink in DOM-based XSS. Eval executes a string as JavaScript code. This makes it extremely dangerous, especially when used with user input. In DOM-based cross-site scripting, The attacker identifies a vulnerable data flow where input from a source is passed directly into a sink without validation or sanitization. They then inject malicious data at the source, which flows to the sink and ultimately compromises the user's or the victim's browser. Let's discuss another type of XSS called blind XSS. This is a form of persistent or stored XSS, but the key difference is that it impacts backend or internal users such as admins. In a blind XSS attack, the attacker stores a malicious payload somewhere in the application, for example, feedback from a support ticket, which is later accessed and executed by the internal user in a different interface such as an admin dashboard. The key characteristics of blind XSS is that the result of the attack is not directly visible to the attacker, making it harder to detect, and also it would be harder for the attacker to perform this attack because the attacker can't see what is the outcome. It is often used to exfiltrate data silently from internal systems. So what we have discussed up until now is a bit of a high-level technical views around what is cross-site scripting and what are different types of it. So now let's jump into some hands-on labs and let's practice how we can hunt for cross-site scripting. Okay, so for our hunting for cross-site scripting section, we are going to use Portrigger. Portrigger is a company behind WebSuite where they have a lot of interesting material and learning materials and labs in their website. So what you need to do is head to their website, go to Academy, and just click on that, and then you'll get all the different topics and all the contents. I will just directly go to the labs because that's what we are going to focus, and then you can see there is a lot of different topics, and they also cover some learning materials in here that you can see, and for instance some labs that we have here. So for the first lab, I'm going to focus on stored cross-site scripting. We saw how reflected cross-site scripting works, and here we want to see how a stored cross-site scripting works. So all you need to do is to create an account with Portrigger, which is free, and then you can access the environment and access the lab. So here it says the lab contains a stored cross-site scripting vulnerability in the comment functionality. To solve this lab, submit a comment that calls the alert function when the blog post is viewed. So if you head to the application, you can see that it's a blog, and then it says view my post. So you can see that we have a range of posts here. You can go to view the post, and there is a comment section here. And so this is a stored type of cross-site scripting, because what we need to do is to submit a script and submit a payload, which will be then stored in the application, and similar to what we can see in here, that we see other people's comment. Everyone else that visiting here will see our comment and will trigger the cross-site scripting. So let's use that simple payload that we used for the reflected cross-site scripting and see if it works. Okay, so I'm gonna submit this, which is the simplest cross-site scripting, and just for the name and test, I can say test, and okay. And here it says you have solved the lab. If I go to the blog, you can see that it triggers my cross-site scripting because I'm visiting this page, and that is part of this comment that has been executed. So whoever visits this section will see my comment because the application is vulnerable and a malicious node has just submitted it. So if I refresh that page again, you will see that it will show up again. So let's move on to the next lab. Okay, let's jump into another lab where we want to talk about the DOM-based XSS. Here what we can see says this lab contains a DOM-based cross-site scripting vulnerability in the search block functionality. It uses an inner HTML assignment which changes the HTML contents of a div element using data from location.search. To solve this lab, perform a cross-site scripting attack that calls the alert function. Okay, so if we go here, we see that, and of course we have the search button. So if I go with the usual way, so I'll just say, let's do script, and then say alert, and see what will happen. Okay, so as you can see here, nothing actually is happening, and you can see the payload we put in here appears here. So what we can do is that, let's see how is the source code. Okay, if we go to the source code, and then you can see here it says 0 results for the search, and then we have the search message, and if you go here, you will see that the function do search query, it populates something in there, it receives the query and then populate it there, and then we have the location.search which we read and then pass it to this. So technically it reads that and then passes it to this function to show. But why our script is not working? Because there's no sort of validation in here. The reason is that payload is been put inside another sort of a span, and technically the browsers wouldn't execute a script, and they would not allow to embed scripts like that. So what we need to do is to come up with a different payload. So for that, there are multiple sources for XSS payloads. You can just simply Google it. I'll just go with the first option. There are multiple, you can see payloads in here that you can go. I'll use the image one. I'll use the image source and error to prompt something. So let's see if that payload will work. So we paste it here, we go for search, and it shows up, right? So, and it's successful in here. So you can see that now we have seen a successful DOM-based cross-site scripting. Our value has been put it here, so you see that the value has been followed from the source to the sink. So our source is the search value, and the sink is where we put it in the inner HTML value. And there are different payloads, like you can also use iframe, and it would do the same. It's just a matter that it should be something that the browser will allow you to execute in there. Cool. That's our second lab. Let's jump into another lab to practice even more. This lab demonstrates a reflected DOM vulnerability. The reflected DOM vulnerabilities occur when the server-side application processes data from a request and echoes the data in the response. A script on the page then processes the reflected data in an unsafe way, ultimately writing it to a dangerous sink. We talked about sources and sinks in the video, and here we are gonna play a bit more with them in a bit of a more detail. To solve this lab, create an injection that calls the alert function. So let's jump into that. Here I have my Burp Suite up and running, and the traffic has been intercepted. So as you can see, we have a search function. Let's search for something. And this is because of the Burp Suite. And we get no results, right? So let's look into what's being communicated through Burp. So we have the search function that you can see here, and then after it we got a request for the search result.js, and then we got another call. So let's see what's happening. Here's the response from the server for our first request that we see that we have the search test, and an interesting thing here is that it is calling search results, which is a resource under the same web application in the resources.js, and that's what you can see in the second packet that we've requested. that's actually the JS that we've requested, and it's actually downloading and performing some tasks. And after that is probably this one as making another call, which is under search results, and then search, and then the parameter that we have. So let's look into our search results, the JS script. So as you can see, it's creating a XHR, which is technically Ajax, allowing us to call without reloading the page. And it says if the response is fully loaded and if the response status is okay, then technically it creates a variable search results object and then add it with this response text, and it's using eval. So that's very interesting because using eval is very dangerous. Eval is very dangerous in JavaScript and normally should have been avoided, but we are using it in here, and once we get the response, we are passing it to display the search results. So this is probably then we have the open and send request, and that's probably where we having this function and this packet called. Let's play around with this a bit. We send it to the repeater. Here we're saying the get search results and then the search. If we send this to get the response, we see that it's a JSON file. It's technically reflecting what we have put it there, and that's correct because basically here it's also expecting JSON, and that response.text is JSON. What we want to do is that we want to escape, and we want to add something in here so that we can run the eval function, right? So we can see what will happen when we run the eval function. So here we're saying search name is just test and test. So if I want to play around with this a bit, I have to see what payload I can send so that it will escape this and will exit technically this. So what I can do is that in the request that I'm sending, I can add a double quote to escape, and then I will add space and then say alert 1, and that's it, right? So we also need to URL encode this and send it to the server. So as you can see here, the server response is interesting because the server is actually escaping our character. What we can do is that we can escape it ourselves using a backslash and then just send it to see what will be the server reaction on this. Okay, so that's interesting. As you can see here, now we successfully managed to create escape, and technically we are creating two values. So the problem here is that it's not a correct format because we also have a double quotation and the close brackets in here that we need to escape. So what we can do is that we can just comment them out, and then to comment in JavaScript we use this, and of course we have to close the bracket as well. So let's send this one. Okay, so now it seems to be a successful escaping and then a successful JSON format. So we clearly closed what we have opened in here, and then we added and escaped this value, and then we have another variable that we can play with. So let's submit this payload to our browser and let's see what we will get. Okay, it's now working. So let's see if I change this one with a plus. And there we go. Okay, so what happened is that we basically successfully exploited the cross-site scripting. And then technically you can see that the value that we have submitted here will be then sent to our JavaScript and JSON here, and then the eval function. So they technically in here we are rendering it will create that cross-site scripting problem. Okay, so that's this lab. Let's move on to the next. Okay, so let's jump into the last lab that we want to cover in this video. Of course, there are lots of other labs available in the Portugal Web Security Academy, but we're not going to cover all of those. I will create following up videos where I will dive into more advanced XSS examples, and we will practice some of those and some XSS ones in other platforms. So in this lab, we are dealing with custom tags. So the lab is asking us to perform a cross-site scripting attack that injects a custom tag and automatically alerts document.cookie. So here it means that we can't use the existing tags. So let's see if we just simply use a script tag, what would be the outcome? So the server responds with the tag is not allowed. Normally this is the web application firewall blocking us, so that's why it's asking us to create a random and customized tag. So here we can say just give it a random name. We're just saying random, that's to be our tag. And then what we want to do is that we want this to be triggered automatically, right? We want to for the user to quickly jump into this, and then for the XSS to be triggered automatically. What we can do is we can use the onFocus, and then we say onFocus alert. So what we want is we want the document.cookies. Okay, so when we have this, we need to make sure that this is automatically being triggered. For that, we need to add an ID. Just we say the ID X, and then we say we just need to make sure that this focus item can be triggered, right? So we also have tab index equals 1, and it's double quote, right? We say equals 1, right? So this is what we need to look for, and then you can see it passes our firewall. So that means our random or our custom made tag is working, but the cross-site script has not been triggered. Why? Because we haven't called the ID, right? So what we can do is that we can have hashtag X, and that will trigger an onFocus, and then it will trigger the document.cookie. What we can do next is that we need to go to the exploit server, which is there in the Websuite Academy. So what we can do is that we need to deliver this as a body, but the body needs to be something that redirects the user, right? So we create the script in here. We just close that script, and we want the script to basically do a redirection, right? So we just say location and then this. So let's deliver exploit to the victim, and it says we've solved it out. Okay, going back to our theoretical discussions, let's discuss how we can prevent XSS attacks and how you can protect your application. First thing first, input validation. Input validation is the process of verifying and checking user-supplied input before processing it. Input validation should be performed on both server-side and the client-side. Do not rely solely on the client-side controls. An attacker can manipulate what it gets submitted by passing browser-side controls. Therefore, always validate on the backend as well. What should be validated? Length. For example, if the input is a mobile number, it should be exactly 9 digits. If it's a state abbreviation like in Australia, it might be limited to 3 characters. Format. For fields like email addresses, validate that they follow a proper format. Example, some characters at some characters dot something. You can use regular expressions or regex for this. We will talk about this in a different video. So we also can talk about allowed characters. For example, if the input is a mobile number, you should only allow digits, no alphabets or symbols. Another important concept in input validation is whitelisting versus blacklisting. Whitelisting allows only predefined patterns, and everything else is rejected. That's default deny. Blacklisting block known bad patterns but allow everything else. So that's the default allow. Whitelisting is normally preferred in most cases because it's more restricted and it's more secure. So you define only what you want to pass through and then by default block everything else. So the next method to prevent cross-site scripting is output encoding. Remember that in XSS, untrusted input flows through the application and ends up in the victim's browser. So it's critical to apply controls at every step. Output encoding ensures that any potentially harmful input is displayed as plain text rather than being interpreted and executed as code by the browser. Here are some common types of output encoding. We have HTML encoding, JavaScript, attribute or URL encoding. Each type is used depending on where the data is being rendered. For example, use HTML encoding when outputting data into a web page. Use attribute encoding when inserting data into HTML attributes like href or title. And use URL encoding when passing untrusted input in query parameters or URLs. The next method to prevent cross-site scripting is input sanitization. So you might be wondering what's the difference between input validation and sanitization. So that's a great question. Input validation is about ensuring the input meets expected criteria such as length, format, or allowed characters. Input sanitization, on the other hand, is about cleaning the input by removing or escaping potentially dangerous content. In sanitization, we modify the input, for example, by removing harmful scripts or special characters to make it safe before using or displaying it. The next method to protect against XSS, and basically this method is more like reducing the impact, is cookie security. So another layer of protection involves ensuring the security of cookies. While it does not prevent XSS from occurring, it can significantly reduce the impact, especially for attackers targeting session theft. Here are some of the key cookie-related security flags. HTTP only. So it prevents JavaScript from accessing the cookies, which can mitigate XSS-based session hijacking. Secure flag ensures cookies are only sent over HTTPS, protecting them from interception. Same site restricts how cookies are sent with the cross-site request, helping preventing CSRF attacks. Content type and X-content type options help ensure the browser interprets responses correctly and does not render malicious content in unintended ways. And the final way in protecting is content security policy. The last method that we've discussed. Like cookie flags, CSP is another impact reduction strategy. It won't stop XSS vulnerabilities, but it can limit what an attacker can do if XSS does happen. CSP is a browser-side security feature that allows you to define which content the browser is allowed to load and execute, including scripts, styles, images, fonts, and etc. For example, if you set your CSP header as scripts or self, then only scripts from the same origin as this application will be executed. This blocks attackers from injecting and executing scripts from untrusted sources. Okay, in this video, we discussed XSS in detail. We started by explaining what XSS is, explored its real-world impact, and looked at the various types of XSS. Then we moved into hands-on lab, where we put into practice everything we've learned. Finally, we covered how to protect applications from these attackers and from these attacks using multiple prevention techniques. There will be more technical videos on XSS coming soon, including XSS attacks in bug bounty programs, more advanced exploitation, and bypassing mechanisms. So stay tuned. If you enjoyed this video, please hit the like button and subscribe to my channel. Thanks for watching the video. Stay tuned and see you in the next video.